Okay, I will give you a talk about the latest advancements in the GPU ecosystem. It's the right time for this talk at this event because last week there was a GTC conference in San Jose, and we did a lot of announcements, and I could include these kind of announcements. At the GPU technology conference, more than 3,000 people attended, more than 600 talks were there, and this gave a very good overview about the latest status in the GPU ecosystem and the latest developments. You will find later this month the presentations online in PDF and also the videos, so you can have a look if you were not able to attend. So what's the outline of this talk? I will give a little bit of overview about a new feature in the Tesla K40 GPU, the so-called GPU boost feature. Then we did a very nice announcement with the Jetson TK1 development board for embedded HPC. Pascal GPU were announced, so the next generation after the Kepler GPU with some nice features like the 3D memory, stacked memory technology. Gilad mentioned the NVLink technology, which I will show you on the slides. CUDA 6.0 is currently in early access. Production release will come in the next couple of days. Some nice features like the unified memory, I will explain, the extended library interfaces, and also GPU direct RDMA support with OpenMPI, and some slides at the end about the future of programming development. So the Tesla K40 GPU is a latest GPU version which was announced a couple of months ago. It gives you faster cores, it gives you larger memory, 12 gigabyte instead of 6 gigabyte, so you can run larger input sets on the GPU, which is very nice. But we also introduced a new feature, the GPU boost feature, and this features use the extra power headroom for unlocking extra performance. What does it mean? So we did some power measurements for a couple of applications like Amber or Gromax or LAMPS and so on. And what we saw is that more or less all the applications are using around 100 to 150 watts of the GPU power. So the specification for the GPUs is 235 watt. So we have extra power headroom, and we can convert this extra power headroom to higher performance. So the base clock here is 745 megahertz, so for worst case workloads like DGEM operations, etc. But we have introduced two so-called boost clocks. So one for the K40 is 810 megahertz, and the highest boost clock is 875 megahertz. So you as a user can increase the clock for your workload, and you get additional power. How can you increase the clock? You can do this by the Nvidia SMI interface, so you can query the supported clocks with the NVIDIA SMI interface, and you can set the memory clock and the graphics clock according to your workload. And this is also possible with the C API or with the API with the NVIDIA Management Library. So the difference to the boost clock for the GeForce cards is that you have here for the HPC Tesla workloads a deterministic clock, which is not available here with the non-Tesla cards. Okay, another announcement we did at the GTC Technology Conference is the Jetson TK1 development board. Its main focus is for the development of embedded computer robotics, medical imaging, etc. It's based on the so-called Tegra K1 SoC, which was announced earlier this year at CES in Las Vegas. So it's a combination of the Kepler GPU with 192 cores, with a compute capability of 3.2, so that's the same like we have with the Tesla cards. And also integrated is a ARM Cortex A15 CPU, so 4+1 cores. In addition, you have 2 GB of memory, you have a lot of I/O options, mini PCI Express slot, gigabit Ethernet, HDMI connector, USB 3.0 port, and so on. And the good thing is that it's fully supported by the CUDA Toolkit 6.0. We are providing OpenGL capabilities, and also the OpenGL ES 3.0 standard will be supported. It runs 30-bit Ubuntu operating system. So the Tegra K1 was announced in 2 versions, the 32-bit version, and later this year there will be also a 64-bit version available. So all in all, 326 gigaflops in 5 watts will be provided, and the price point is $192. So you can pre-order this board, this development board at this website, and you will redirect it to our partners like Seco and others. Another announcement was the announcement of the Pascal GPU. So it's a HPC board, so optimized for double precision floating point operation. It has integrated a very high bandwidth 3D stacked memory on package. I will explain this a little bit later. Also, it will integrate the NVLink technology, which is a high bandwidth technology for the communication of CPU to the GPU and also between GPUs inside a system. It will provide unified memory hardware support. I will cover this also a little bit later. Interesting that new packaging allows much denser solutions, so it's 1/3 the size of the current PCI Express board. You see here a sample of this Pascal GPU. So stacked memory, what does it mean? Multiple layers of DRAM components will be integrated on the package along with the GPU, and there are a lot of advantages. So we have 4 times higher bandwidth compared to the GDDR5 memory today. With the Tesla K40, we have around 288 gigabytes per second, so we are reaching the teraflops bandwidth. terabytes per second bandwidth, we have larger capacity, and we discussed yesterday the energy efficiency for exascale supercomputer. So stacked memory provides us 4 times more energy efficiency per bit. So another technology which is integrated is the NVLink technology. It gives you higher bandwidth than the current PCI Express technology. It's a high-speed interconnect inside a system for the connection of CPU and GPU and between GPUs. There are basic building blocks, so-called bricks, which is an 8-lane differential bidirectional link, and multiple links can be aggregated to increase bandwidth, so that NVLink will provide a bandwidth of 80 to 200 gigabytes per second compared to the 16 gigabytes per second of the PCI Express Gen 3 today. It preserves the PCI Express programming model, so the CPU-initiated transactions such as control and configurations are going over the PCI Express connections, and all the GPU-initiated transaction uses the NVLink. Especially with the unified memory feature, it gives you much higher performance and gives you a much more optimized system. So here you see some examples for configurations. So we have a CPU connected via different links here, NVLinks to the GPU. So IBM, for instance, announced together with Nvidia at the GTC the NVLink support for the power CPU, and we will see much more announcements in the future. And NVLink is also able to connect several GPUs inside a system which are also connected to the CPU. And also, if the CPU does not provide support for NVLink, we can use NVLink technology in order to integrate, to connect the GPU inside the system via this high-speed interconnect. I talked about unified memory. What does it mean? So today, the developer has a view on the CPU memory, on the system memory, and the GPU memory, and he has to transfer the data manually, so he has to program the data transfers. Unified memory, supported starting with CUDA 6.0, gives you a common view, developer view on a unified memory. So in this example, you see here a code which with unified memory supported. What does it mean? You have to define in the 6.0 version CUDA malloc managed area for this point here, data, and you don't have to allocate the data by hand, or you don't have to program the allocation by hand, or you don't have to transfer the data by hand. This will be done by the runtime system and by the driver system. So it simplifies the memory management a lot, and here on the left-hand side you see a CPU code. So it looks very similar to the CPU code, and it gives you much more easier access to the for the programmer. Okay, so it simplifies the programming and memory model. For instance, you have single pointers to data, and you can access these pointers from CPU, also from the GPU. It gives you better opportunities, possibilities to integrate the parallel programming model into the languages, future languages. I will cover this a little bit later. And what's very important for beginners of programmers which will start with the CUDA programming. It simplifies the code porting. So you will also have the API available. So in order to tune your code, you can do it by hand, but this is a topic of the performance optimization, and it's no longer needed. In terms of roadmap for unified memory, we started with a CUDA 6.0 release, where the production release will become available in the next couple of days. So single pointer to data, no mem copies are required. You have a coherency at launch at sync time, CUDA syncs, and it's especially good for deep data structures. You don't have to take care about the copy to the GPU and from the GPU. So next we will provide optimizations for this unified memory model, for instance prefetching, migration hints, or also additional OS support. And with future GPUs we will also provide hardware support for this transfers, GPU fault handling, page fault handling, and so on. Okay. Another topic which is covered in CUDA 6.0 is the GPU direct RDMA support with OpenMPI. So it is a Kepler class GPU required. The Mellanox interconnect is required, and CUDA 6.0 early access release candidate, or the final version, starting with OpenMPI 1.74. It's supported. You need the GPU direct RDMA enabling software from Mellanox, which DK Panda also described yesterday. The compilation of the OpenMPI package is very easy, so you have to include the -- with CUDA flag, and the support is configured in if CUDA 6.0, the CUDA header file, will be detected. You can also check if it's included in the package with the OpenMPI info call. You have to enable this because it's switched off by default for this first version with the setting --MCA and so on. And you can optimize the transfers because similar to MVA pitch, we are also have a hybrid model here for OpenMPI. You have this limitation of the chipset where you have good peer-to-peer write performance, and read performance is much slower. So we are using for large messages also the host memory staging. What does it mean? So Without GPU direct RDMA support, we have a latency of around 15 to 16 microseconds for small messages, and we achieve around 6 microseconds latency with GPU direct RDMA support. And here you see the limitation of the chipset. Therefore, we introduced this hybrid version, which scales to much higher bandwidth here. Some application benchmarks with GPU direct RDMA. This HUMD benchmark, which was covered yesterday too, so I can go very fast over it. With a small input set, 16K particles, we achieved here on 4 nodes improvement of 20%, and with a larger input set with 512K particles, we got a lot of more improvement. So on this website there is a benchmark report for this use case, and you will get much more details. CUDA 6.0 also offers extended library interfaces. This means you have an automatic scaling to multiple GPUs inside a node for the QFFT and the QBLASS library. It operates directly on large data sets that reside in CPU memory, and you see here on this example with several Tesla K1 GPU that you get a very nice scaling, in this case on SGEM. You will find much more information about the QBLASS XT or also about the QFFT XT on the websites. There's also a new feature, a new drop-in NVBLASS library. This gives you the possibility to link the BLASS library instead of, for instance, MKL library without changing your code. So you can preload the NVBLASS library, and this library will intercept all the BLASS calls and will direct the BLASS calls to the GPU. You see here MKL on a 6-core Xeon, and scaling of the NVBLASS library with several K20X GPUs. So it's a very easy way to bring applications without any modification of the source code to the GPU. In this case here, it was a drop-in speed-up for the R statistical package. Another feature which we introduced is the remote development capability with the Nsight Eclipse edition. What does it mean? You can edit your code on the local workstation on the laptop, and you can sync automatically your work and can build, run, debug, and profile your application on the cluster. So it's used via SSH, this automatic sync, and it works very fine and helps the programmers a lot. What's next? So our goals for the CUDA, for the GPU ecosystem, are these, more or less these 4 goals. So simplicity, so it should be very easy to use parallelism. Productivity, of course, it should give you very fast access to the GPU, especially for the development of codes. Portability, so you should write codes that can execute on all targets, and of course for high performance computing, performance is always a goal. performance, absolute performance, and also scalability. So we are working very hard in order to make heterogeneous applications much more easier to program. Currently, you have more or less two programs or one program, and hybrid code or GPU code goes to the GPU and the serial code to the CPU. So in future, we want to have a single program, and we want to abstract all the heterogeneous execution via the runtime or via a virtual machine, so that ultimately the parallel workload goes to the GPU and the serial workload goes to the CPU. Therefore, we are working together with a lot of language standardization organizations, for instance, with the C++ standardization organization, or with Fortran, or also with Java, in order to bring parallelism into the language standards, so that you don't need CUDA or OpenACC or other GPU languages to use a GPU. The parallelism should be included in the language standards. And for instance, for C++, we made a proposal for a parallel algorithms library, and this was also accepted by the C++ standardization committee. So this will possibly integrated into the C++ 2017 standard. So this means you have here your parallel constructs in the code, and you can compile to the GPU or to the Xeon Phi or to the multi-core CPUs, and you don't have to program anything special for the GPU. Also, I was very surprised how many people in HPC, meanwhile, using Python, not only in bioinformatics, also in other scientific areas. So, and with the NumPy compiler, there's a free and open source compiler available for array-oriented Python, which means that you can program in CUDA with a Python syntax, and this increases productivity a lot, and we will see much more on the Python front regarding HPC and regarding support for GPUs in the future. Also, we are happy that the OpenACC implementation in GCC just started last year. Meanwhile, the first versions are integrated in the trunk, and we believe that in later this year, the OpenACC will be fully supported by GCC and not only by the commercial compilers from PGI / Nvidia, from Cray or from CUPS. Another field is the big data, Hadoop support for GPUs. So IBM is working very hard to implement, for instance, Java on the GPU and to support, in this case, Hadoop for data analytics and so on. I mentioned Java, so also there was a talk at GTC about the GPU support for Java from Vinod Grover from Nvidia. You can look to this talk more in detail, but it gives you a very nice speed up with using GPUs, and Vinod describes a lot about the approach to bring or to compile Java with a GPU support. Okay, so that's also my last slide. It was right in time. Here's a nice pointer to the nice blog, the Parallel for All blog, which our colleague Mark Harris writes, and you can download here, for instance, a lot of CUDA casts, so videos, or there's a area for CUDA pro tips, so for useful techniques or other stuff around GPU computing, new developments for the programming models for GPUs. Okay, that's all, and I'm open now for questions.
About the NVLink feature in this, IBM previously talked about their own co-processor interface. Mentioned it, coherence, something.
It's a copy interface. Yeah.
How are NVLink and
Yeah, so with the next generation, with the NVLink 2.0, we will also support a cache coherent interface, and we will use the copy interface.
So those are basically
yeah, that's right. Any other questions? Yeah, please.
Sorry for all those questions. Why? I mean, every time I see an advancement in graphics, I ask myself, okay, why we don't see some advancement in sound too? Because there are kind of similar concepts. I mean, there are frequencies in sound and there are frequencies in light. So we have visuals and we have hearing stuff. So, like for example, I can think of applications like active noise control, things like that that could be done in GPU. Why NVIDIA is not, getting into that direction too?
We are going also in this direction. For instance, we're working together with Shazam. Maybe you know this application where you can play a song, and Shazam will detect the song. And Shazam is, for instance, using GPU technology for detecting the titles and the songwriters. So we are working together with partners like Shazam also to bring GPUs into these areas. So, but we are not a sound company, I would say. So we are concentrating, we are focusing on visual computing. That's our first focus. Okay.
Okay, great. So,
thanks.
Thank you very much.